All right, so this is Geometry B, Unit 5, Area, Lesson 3, Areas of Regular Polygons. You recall the definition of regular is congruent sides and congruent angles. So regular means all sides congruent and all angles congruent. So I've got on the screen a regular pentagon, pent meaning 5. That's the Greek prefix, pentagon. And it's got 5 congruent sides. All the sides are about pretty close to 7 units long. The angles are all the same as well, right? The key to finding the area of a regular polygon is this. It is dividing it into triangles. And we do that by drawing something called a radius. You can see I've got the pentagon superimposed or inscribed in a circle. And the radius is the distance between a vertex and the center. The vertex and the center. Okay? And this has 5 radii that are all the same. Okay, now it just so happens I drew this circle to have a radius of 6. So that is what I'm going to work with here. Sometimes you're told the radius, sometimes you're told the side length, sometimes you're told the apothem, and that's a word I'm going to get to here in a moment. But these are all radiuses. And you may recognize the Plymouth or Chrysler, actually Chrysler automobile logo there. All right, so those are radius or radii. This is a radius, and in this case the radius is 6. Okay, and I want to find the area of the regular pentagon here. Okay. So one of the things I'm going to do is I'm going to recognize that the number of degrees in a full circle, the number of degrees in a full circle is 360 degrees. So if I go all the way around, that's 360 degrees. So if I take just one of these, that's 360 divided by 5. 360 divided by 5. 360 divided by 5 is 72. Okay, so each each vertex angle of these isosceles triangles is 72 degrees. Okay. Now I'm going to draw another segment here that we're going to call the apothem. So let's do that here. The apothem. The apothem is drawn from the center of the regular polygon down to the midpoint of one of the sides. Down to a midpoint of one of the sides. This is called the apothem. Apothem. Okay, and you'll notice it's drawn to the midpoint of one of the sides, and we can use various means to prove the triangles are congruent. I'm not going to go there here. But being congruent triangles means these are right angles. Okay. These are 2 congruent right triangles. And what's more is I can figure out the small angle here of the right triangle because it is that 72 degree angle divided by 2. 72 degrees divided by 2, or 36 degrees. Okay, so there we have a right triangle with a 36 degree angle. And I happen to know the radius is 6. Maybe 6 inches if I'm going to put units on it. Okay? All right, so there we have it. We have a right triangle where we know one of the sides and we know 2 of the angles, right? And by hypotenuse leg, we know we can find the missing sides, right? Now, not hypotenuse leg, angle side. Okay. All right, so let's see if we can figure out. I'm just going to sketch this triangle down below here, resketch it here. We've got a 36 degree angle we've got a 90-degree angle, we've got a side that's 6 inches, and I want to find the two missing sides. So I want to find, well, I'm going to call this x. Okay, well, that is, if this is the reference angle, that is opposite x over hypotenuse, 6. Opposite over hypotenuse, if you think of SOHCAHTOA, is so. Sine, right? So sine of 36 equals x over 6. Multiply by 6, and x equals 6 sine 36. 6 sine 36. Okay? And we can get an approximation using Desmos here. Do remember, again, when you're working with Desmos with sine, cosine, and tangent, click the wrench tool and make sure you've selected degrees and not radians. Okay? So 6 sine 36 gives me a side length of 3.5. I'm going to go with 3 significant figure, 3 decimal places. 3.527. 3.527. Okay? What's even better here is I can store this. I can say capital X equals, and now it's stored, and when I bring that back up, it'll remember the value of cap X. All right. That's what X is, approximately 3.527. Now Y, which is the apothem, I'm going to label that A here. I'm going to label that A for apothem. We can find that as well. That's adjacent over hypotenuse, right? Adjacent over hypotenuse is ca. So cosine of 36 is adjacent over hypotenuse. Multiply both sides by 6, and adjacent is 6 cosine 36. So this is 6 cosine 36. I'm just going to change the sine to a cosine. And I get 4.854. 4.854. Okay? 4.854. Now, why did I find both of these dimensions? Well, X here is 3.527, and the whole base of the triangle is double that, right? 3.527 times 2. And actually, let's do this. 3.527 times 2, 7.054. So the whole side length is 7.054. 7.054. And the height, the apothem, is 4.845. And the area of a triangle is base times height divided by 2. So we can find the area of the triangle as base, 7.054, times height, 4.845, divided by 2. And that's one triangle. Okay? And then we can find, once we found that, and I'm going to go ahead and crunch that here, give you a value here. So 7.054 times 4.845, all divided by 2, 17.088. 17.088. That's the area of a triangle. Now the area of the pentagon is 5 of those triangles. 5 times 17.088. Okay, so now multiply by 5. Okay, so I'm just going to hit times 5 here. 85.44. And I'm going to round to the nearest tenth, 85.4. So approximately 85.4 square inches. Now, if I wanted to, I could count the number of full squares, or mostly full squares, inside the shape, and hopefully it would come very close to 85, if you wanted to verify it that way. So notice the triangle trigonometry. You have to use sine, cosine, and tangent to solve for the missing parts. But it all comes down to finding the area of a triangle and then multiplying by the number of sides.